So today I'm going to talk about large time behavior of solutions to 3D MHD system with initial data near equilibrium. This is a joint work with my colleague Wen Deng. So let's first recall what we mean this MHD system. It's a coupled system of this magnetic field with this velocity field. In 3 space dimension, it's a magnetic field equals like B1, B2, B3. And U denotes the velocity field equals U1, U2, U3. And here, this P denotes the scalar pressure function, which guarantees this divergence-free condition of this velocity field. So here, this magnetic field satisfies this transport equation without a diffusion. And because of this magnetic field act on the incompressible fluid, there is a force called Lorentz force on this Navier-Stokes system. And we can always assume this divergence-free condition of this magnetic field. Here, we mainly consider the case when this initial magnetic field is a small perturbation of this E3, and U0, the initial velocity, to be sufficiently small. So the general MHD system can be written in this way, with magnetic diffusion, mu, and viscosity here, nu. In this case, as far as I know, it was first proved by Du and Liang, the local existence and the uniqueness of solutions, of classical solutions to this system with initial data in HS space. Now, they also prove the global existence and the uniqueness for small initial data. In 2 space dimension, it was proved by Sermanche and Thomas the global well-postedness of the system in 2 space dimension with general initial data. So here we assume the density of the fluid equals 1. If we assume the density of the fluid depends on like time and a space variable, we should couple this system with a transport equation of the density function. That's also called an inhomogeneous Navier-Stokes system. It was proved by Abidi and Peku, like small global well-postedness with niche data in the critical spaces. With mixed partial dissipation and magnetic diffusion, which means like in 2 space dimension, instead of here, this full mu Laplacian, this place could be like partial x1 square of B, and this place, instead of nu Laplacian of U, you can replace here by partial x1 or x2 squared of U. In this case, it was proved by Chongqing Chao and Jiahong Wu, the global well-postedness of the system with general initial data in H2. So if we assume this magnetic diffusion equals 0, it was proved by Yang and his collaborators this local existence of solutions of the system with niche data in the critical base of spaces. In the ideal MHD system, which means when this mu equals 0, it was first proved by Bados, Sulom, and Sulom the global existence and uniqueness of solution to the system with B0 be a small perturbation of this like E3 and an initial velocity to be sufficiently small. And very recently, there is work by Chai and Li which simplified this work by using this ghost energy method of Serge-Alinac. Recently, there are also several papers on the vanishing viscosity limit of this viscous MHD system to the ideal flow. The first work is by Hou, Xu, and Yu. They can prove when this mu equals nu, and when this mu nu tends to 0, the solution of the viscous system tends to the solution of this ideal MHD system of IMHD system of the solutions of Bados and Sulom. And again, this paper was simplified by China Li with this ghost energy method. And there are also a paper by Wen and Zhang that can even prove the vanished viscosity of this viscous MHD system to the ideal MHD system when this mu different than nu and mu nu tends to 0. The solution should tend to the Badot solution of the ideal MHD system. And also recently there is another paper by Chai, Lim, Fenghua Lin, and Neda Masmoudi for the vanished viscosity limit for a more general system of this type. So now let's go back to our problem. In our problem, we consider this MHD system when there is no magnetic diffusion, and we are concerned with this problem, like whether or not classical solutions of this MHD system without magnetic diffusion can develop finite time singularities or not. Even in two-space dimension, this problem is not known. So in two-space dimension case, because of this divergence free condition of this magnetic field, in two-space dimension, we can find a potential function such that this magnetic field B equals gradient perp of this potential function. Then because of this B satisfies this transport equation, this potential function phi should satisfy a scalar free transport equation like this. And then this Lorentz force can be reformulated like divergence of gradient phi tens with gradient phi. Fenghua Li introduced me this problem in 2007. And we proved first in three-space dimension when this phi 0 is a small perturbation of x3. And for u0 to be sufficiently small, then we can prove the global existence of small solution to this system. So the main idea of this proof is to use anisotropic lead-over-the-plane analysis to gate this one-time local Lipschitz estimate of the velocity field. So why we should need this anisotropic lead-over-the-plane theory, I should mention later. And in fact, this Erwan Lipschitz estimate of the velocity field is not required for the existence proof that was observed by Fenghua Lin and Zhang, so that they can have a simplified proof of this result. In general, in two-space dimension, if we assume this sort of a strange admissible condition for the initial magnetic field, like this integral of this difference between B0 and E3 restricted to the trajectory of this B0, d of t equals 0, for all alpha in R2, get rid of this 0. Then we can prove, joint work with Fenghua Lin and Li Xu, we can prove the global existence of solution of this 2D MHD system when this B0 is sufficiently close to E2 and U0 to be small. And we can also prove similar result in three-space dimension. So why this two-space dimension makes so much difference? With three-space dimension, I should mention the reason later. There is another result by Zhang, Wu, and Zhang. They can, in fact, remove this admissible condition here, and also they can prove the decay of solutions. But it turns out, this proof, there is a big gap, which they cannot go through. That's why Zhang wrote another paper for the existence proof in 2D without this strange admissible condition. In three-space dimension, it's rather recent work, my joint work with Hamadi Abidi. In this case, let's denote this E3, like 0, 0, 1, B0 to be a small perturbation of this E3. And we assume this initial velocity field to be sufficiently small in this scalar invariant space. And if this epsilon is sufficiently small, we can prove this 3D MHD system has a unique global solution. And moreover, if this epsilon equals 0, if you assume the additional low frequency assumption for the initial velocity field, we can prove this H2 NH and also the H2 norm of this difference between BT minus E3 should decay to 0, like T to the negative power 1/4. So the motivation for us to study the following result is due to this paper by Califano and his collaborators on Physics Review 1999. In this paper, they made a conjecture that like in two space dimensions, this viscous MHD system, the energy should be dissipated in a rate that is independent of the ohmic resistivity. So which means even if this magnetic diffusion equals 0, the energy should still decay to 0 according to some rate. So that's the new result with my colleague Wen Deng. We indeed can prove result of this type. So let's denote this E3 be 0, 0, 1, and this B0 is a small perturbation of this E3. And we assume this divergence for condition of this phi and U0 to be in the classical circular space Wn01 intersect with this Hn0 for N0 sufficiently large. So in this case, you assume the initial velocity field to be sufficiently small and this epsilon to be sufficiently small. We can indeed prove 3D MHD system without magnetic diffusion has a unique global solution, like C2 solution. And moreover, this W2 infinity norm of the velocity field should decay to 0 according to a rate like minus 5/4 plus kappa. And this W2 infinity norm of this difference between B of t minus E3 should decay to 0, like to the negative power of 3/4 plus kappa. This H2 energy of U velocity field and also this Bt minus E3 of H2 norm should decay to 0 as time goes to infinity according to the rate to the minus 1/2. And also this like H.1 norm of this velocity field decay to 0 to the C to the T minus 1. I might have forgotten to mention you the decay rate here already corresponding to the limiting case of the decay rate by Zhang and all the others on the papers on general function analysis here. So it's easy to observe this our new decay rate is much faster than the rate we obtained before. And in fact, this decay rate could be optimal in the sense that like this decay rate coincides with the rate of the linearized system, which I'm going to present later on. We can also work on the decay rates of high-order derivatives of solutions of this system. So before outlining the proof, let me give you some motivation why we should use Lagrange formulation of this system, and we also need to use anisotropic leader-of-the-pair analysis. So I would like to also take this opportunity to thank Professor Yang Yu-Shiman, which I learned from him for a long time for this anisotropic leader-of-the-pair analysis. So the linearized system of this MHD system can be written in this way, like YTT minus Laplacian YT minus partial 3 squared of y equals f. For this system, the corresponding symbolic equations to this system can be written in this way, lambda squared plus modulus cosine squared of lambda plus cosine 3 squared. So here this cosine denotes like cosine h, cosine 3, and cosine h equals cosine 1, cosine 2. And this equation has two different eigenvalues, like lambda plus and lambda minus. So it's easy to observe this Fourier modes corresponds to this lambda plus, it decays to 0, like heat kernel e to the negative t cosine squared. But this lambda minus cosine, which can be written in this way, decays tends to this minus 1, as cosine tends to infinity only in this cosine 3 directions. Only in this cosine 3 directions. And in fact, this analysis also depends if this is a positive sign or not. If this is negative sign, then these Fourier modes always decays like e to the negative t of cosine squared. So that's why it's reasonable to decompose the frequency space into two parts. One part is like cosine square less than or equals to 2, modulus cosine 3. And the other part is like cosine square greater than like 2 to the cosine 3 square. In this case, because this power is less than minus 4 cosine 3 square, so this part should be imaginary. So for this part, the Fourier analysis should be simpler. But for the remaining part, because of these decaying properties as cosine goes to infinity, only in cosine 3 direction we have to use detailed anisotropic Lie-Doppler analysis. And it's well known in general, it's not correct to propagate these anisotropic regularities for hyperbolic system. It's only true to propagate this like conormal regularity or striated regularities for hyperbolic system. So that's why, due to this difficulty, there is hyperbolic system in this coupled equations. This motivates us to use this Lagrange formulation of this system. So in order to use this Lagrange formulation of this system, the first step is to get rid of this pressure term from this equation. By taking space divergence of the velocity equation, we find that this Laplacian P should satisfy equation of this type. Then this divergence B equals 0 and the divergence U equals 0 will be reduced to the initial data like divergence B0, divergence U0 equals 0. So now let's define this Lagrange trajectory, like capital of xty in this way, as usual. D over dt xty equals U of t xty. Because of the divergence free condition of this velocity field, we have this determinant equals 1. And furthermore, if we take partial derivatives of this like xi with respect to yj, we find that this entry of this matrix should satisfy an equation like this. Now let's multiply on both sides of this equation by b0j and a summation for j between 1 and 2. We find this quantity should satisfy an equation like this. And on the other hand, because of this transport equation for this magnetic field, we find that this restriction of this bi on this Lagrange trajectory should satisfy an equation like this. Then due to the uniqueness of solutions of this ODE system, we find indeed this bi restrict on the trajectory should equals the directional derivative of xi in this direction of b0. So one can find this kind of formulation in the book by Maida and Patazzi. Now for any smooth function by chain rule, we find that this partial f of xty partial yj should satisfy an equation like this. If we denote this matrix A of ty by this partial x over partial y, then by multiplying this inverse matrix on both sides of this equation, we find that this Eulerian like derivative of this f restrict to the Lagrange trajectory should be equals, like this transpose of this A times gradient of y f xty. Then we can calculate explicitly this Lorentz force, B of I, B of j partial of j, B of I. This term is nothing but this second directional derivative of xi along this direction of b0. So now let's introduce this notation. If we denote this capital Y, Ty is the difference between this xty and y. And this bold U of Ty equals the velocity, restrict on the trajectory. And we denote this bold B of Ty equals B, restrict on the trajectory. And a similar notation for the pressure. And A, we denote this inverse matrix of this gradient partial of x over partial y, and then we denote this gradient of y, capital Y, by this. So with this notation, we can find if we already have this Lagrange trajectory, we can find this bold B of Ty in this way. And moreover, this capital Y should satisfy equation like this. Now the difficulties arises because of this term. By energy method, you'll find this term is a good term when you perform energy estimate for this equation. But the difficulty is because of this variable coefficient of this problem. Although this B0 is sufficiently close to say E3, you cannot replace this term by partial Y3 squared of Y and take the remaining term on the right-hand side. If you do like this, you cannot control the remaining terms on the right-hand side. So in order to handle this difficulty, we use an argument of Frobenius type theorem. So in order to do this, we make this technical assumption, like with X3, we have compact support properties between B0 and E3. So with this assumption, we can almost copy this Frobenius argument from the book, like by S.S. Zhang. We define this dy1, dy3 in this way, and dy2, dy3 in this way, and y3 equals w3. Make this change of variable from y to w. Then we already straight this partial B0 vector. In order to make it to be unit vector, we needed to make changes of variable as follows once again. So it's easy to check, like partial B0 of f can be written in this way. After this changes variable, we can find this term is nothing but this partial f of yw along this direction of partial w3. To make this to be unit vector, we use this changes variable from w to z again. Then we can also find these derivatives by chain rule, and if we denote this b of z in this way, this gradient of y should equal gradient of z, which equals b, the transverse matrix of this b times this gradient of z. It's easy to observe when this B0 is sufficiently close to E3. This b of z should be close to the identity matrix. So now we can reformulate the system in this way. Because of this changes variable, the other difficulty is because of this Laplacian, but we are not afraid of this Laplacian. This Laplacian is Laplacian in all directions. So after replace this gradient of z dot with gradient of z by Laplacian, we have this. Because of this Laplacian is Laplacian in all directions. We find this coefficient is in fact close to each other. So we are not afraid of this term. So we already rounded the difficulty of this variable coefficient for this partial B0 squared of y. The next difficulty to prove this global existence and also decay properties of this system is because of the right-hand side of this term, which is independent of time t. So in order to study this decay rate of this system, we have to introduce an correction term like y tilde. So we can denote this y equals y tilde plus y bar, with this y tilde satisfying equation of this type. This y tilde is independent of time, so like take partial z on both sides, then you find this y tilde indeed satisfies equation of this type. So after we get rid of this correction term, we find that this y bar should satisfy an equation like this, ytt bar minus Laplacian of z, yt bar minus partial z squared of y bar with the source term. And we are very fortunate, like this main part of the source term keeps the structure of the original system. Like before, here, it's partial B0 of y times with partial B0 of y. After this correction term, this term is still like partial 3 y bar times with partial 3 of y bar. Why is this partial 3 is so important? I'm going to mention later. And this term is the same as before. So this structure is purely because of this structure of this nonlinear system is because of this divergence precondition of this B, and also the divergence precondition of the velocity field, so that still it keeps this original structure. So before I outline the proof, let me recall you some notation, like F, WNP norm, the classical subleft norm. This L, P, K of N norm denotes the decay of this WKP norm, NP norm of this UT with decay rate like minus K. In the particular case, when P equals 1, P equals 2, and P equals plus infinity, we can simplify the notation as follows, like 3 lines of N denotes WNY norm. This 2-line norm of F of N denotes this HN norm of F. And this 1 line of norm of N denotes Wn infinity norm of this F. And this 2-line norm of Kn denotes this Hn decay of this U with decay rate minus K. And this 1 line of this UK norm denotes this Wn infinity norm decay with rate minus K. So now the result for this Lagrange formulation can be formulated as follows. As long as this initial data in this WNL0 1 norm, and also this initial data in this HN0 norm to be sufficiently small, and this epsilon to be sufficiently small, we can prove this Lagrange formulation indeed has a C2 solution. And moreover, the derivative in partial 3 direction, 3/2 minus K1, which means this W1 infinity norm of partial 3 y bar decays to 0 according to the rate, like 3/2 minus kappa. This W2 infinity norm of this yt bar decays to 0 according to the rate minus 5 plus kappa, and y bar itself, W2 and infinity, decays to 0, like to minus 1/4 plus K. So from this decay rate, you indeed find these dissipative properties of these solutions along this direction of this magnetic field is indeed much faster than the other directions. And that's why, like in 2-space dimension, you can avoid use anisotropic linear dipole analysis. Because along this direction of this magnetic field directions of this velocity field should decay very fast. And the other way is to use divergence precondition. So combine these 2 properties in 2-space dimension, you can avoid using this anisotropic linear dipole analysis. But however, in 3-space dimension, you only have one direction which is better than the other directions, and you only have this divergence precondition. You cannot recover the decay rate of the other two components. And also in subleft norm, we also prove the following decay rates, which I'm not going to explain. So once again, before the presentation of this proof, I'm going to recall you this famous theorem by Serge Kleinemann at the beginning of the 1980s. So he considered, in a serious paper, he considered this involution equation of this type, U of t minus L of u equals f of u, d of u. So here this du denotes ut, ux1 to ux of n. So here, this L denotes a linear differential operator with constant coefficient. So under the following assumptions, like L satisfies the dispersion condition of the flowing type, and also the linearized solution of this linear system decays according to the rate, like minus k0. And furthermore, if you assume this growth rate of this source term, like according to the rate, p plus 1 for this modulus of p plus modulus of d of u to be sufficiently small. When this p and the decay rate of the linearized solution satisfying the following condition, such Kleinman can prove the general theorem concerning the existence also decay rate of solution of this type. So recall you that the nonlinear source term in our equation is basically term of this type. This is the perturbation term. And the main type is of this type. The growth of the derivative is like quadratic growth. Although we are cheating here because there is a double Ries transform here, which does not map continuously from L infinity to L infinity. So even if we have this double Ries transform maps continuously from L infinity to L infinity, here correspond to this P here, we only have this P equals 1. And the decay rate for the linearized solution, which we can prove later, corresponds to this K0 equals 1/2, 1, and 3/2, which is far away to satisfy this condition. So that's why no way you can apply the theorem of Kleinman type to our system. But fortunately, this idea of using this Hammond version of Nash-Moser iteration scheme still works in our case. So in order to do this, the first step is to study this decay rate of the linearized system. For this linearized system, we can indeed prove this direction along x3, like Wn infinite norm, decays according to the rate, like t to the -1. And this partial of ty decays to 0 according to the rate, like 3/2 minus delta. And y itself decays to 0 according to the rate, like t to the -1/2. And we can also prove this energy estimate for this linearized system. And we even can prove this time-weighted energy estimate for this linearized solution. So this also tells you, this kind of estimate also tells you that along the different direction, this solution should decay to 0 according to different rates. And here, I have a strange norm here, which I should explain you later. So the main idea of the proof is to use Fourier transform. By taking Fourier transform on both sides, you can solve explicitly this y of ty equals gamma t of d act on y1. That's Fourier multiplier. So as we observed before, when we analyze solution of this type, we should split the frequency space into two parts. One part is when this cosine modulus square greater than or equals to 2 of modulus cosine 3. Then this alpha cosine, it's real, and we can write this lambda 1 cosine in this way, and the lambda 2 of cosine this way. Then this fundamental solution, Fourier transform of this fundamental solution, restrict on this region, can be written in this way. That's why the analysis of this part is difficult, because here, this cosine square over 2 minus cosine tends to -1, tends to 1, only in cosine 3 direction. So the analysis of this part, you can expect, is much more difficult than the other part. For the remaining part, because this part is real, now we find this part is in fact imaginary. So we can rewrite this fundamental Fourier transform of this fundamental solution in this way. It's almost like the fundamental solution of the heat kernel. And the analysis of this part should be much more easier. And with the decay rate, with homogeneous source term, we also need this decay rate for this equation with the non-trivial source term and 0 initial data. So here we also, because we will use harmonious version of Nash-Moser iteration scheme, we can assume this g of t is 0 if this t is greater than or equals to this gamma. Then we can also prove similar decay rate with the right-hand side term. So the proof is usual, because we already have this partial 3 gamma t minus s, the decay rate of this solution operator. We can decompose this integral to be 2 parts. One part is 0 to t over 2 here. Then because of the decay rate of this fundamental solution, we find that this should be controlled by like this. Now because s is between 0 to t over 2. So this part should be get rid of this part. That's why we can control this part easily. But for the remaining part, we have to use this energy estimate. That's why we need also to estimate this energy estimate of the linearized solution in order to estimate the source term of the linearized equation. So by combining the above terms, we can obtain the decay rate of this partial 3y. So second step of this method is to work on the energy estimate for the linearized equation. The first step is to derive this source term like f prime of y, this direction, a derivative in this x direction. So we indeed, because Guillaume already given the source term explicitly in the nonlinear equation, we can find this derivative can indeed be written in 3 forms. This part, f1 and f2. f0 is related to this one, and f1 related to this pressure term, and f2 related to this yt. So f1 is related to this partial 3 of y, and f2 is related to this y of t. So the calculation is like standard Gauss derivative. We have this chain rule. With this chain rule, we can calculate explicitly this derivative of functional derivative of this f0 and also f1 and f2. The next step to work on this problem is to estimate of this f prime y of x. As we mentioned before, in order to get the decay estimate of the linearized solutions, we need this Wn1 infinite norm, Wn1 norm of this source term. But as we observed before, there is like double Ritz transform on the source term. So in this case, impossible for us to get this classical L1 norm or Wn1 norm of the source term because of this double Ritz transform. So to overcome this difficulty, a natural replacement of this W dot S1 will be this space of norm B dot 1 norm. Then this double Ritz transform maps continuously from this space to this base of space. And because the source term is usually the product of some nonlinear term, we cannot, when this s equals 0, we cannot estimate of this b dot 0 1 norm of this source term. So that's why we need a little bit of derivative for the source term. That's why when we do work on the energy estimate, work on the estimate concerning this L1 norm, instead of we estimate a G1 L2 norm, we estimate this like 2 delta norm of this G L1 norm. So with this notation like G delta norm, which means like low frequency part, 2 delta derivative, and high frequency part, that n plus 4 derivative. Then we can estimate this f0 prime y of x, this norm, by the replacement of this base of norm, which can be easily estimated on the right-hand side. So that's the estimate of this Wn norm. So the definition of this base of space is classical. It's like this. You have a function which for any torque greater than 0, you have the summation of j belongs to z phi to the power of negative power of j of tau equals 1 for any torque greater than 0. That's homogeneous version. And this non-homogeneous version is chi of tau equals 1 minus of this summation for j greater than negative. And then we can define this frequency cutoff operator as a frequency cutoff such that the frequency of this A is around this annulus with the radius of the annulus is like 2 to the power of j. And we can also have this S of j partial sum operator, which is the frequency cutoff, so that the frequency of this part is supported in a ball with radius 2 to the power of j. Then we can define this space of norm B dot SP of R like 2 of G of S. You have S derivative, and LP, that's integrability estimate, and this LR, the summation with respect to this J. So that's a classical definition of this space of space. And as we mentioned before, not only we need to estimate this Wn0, one norm of the source term, we need also to estimate this H, like n plus one norm of the source term of this type. For this part, although it's so much complicated, it's not so mathematically, it's not so much difficult. You just need to use multi-type inequalities, and you can eventually find this estimate. You can also estimate the second derivative of the source term, like Hn norm, and also this Wn1 and the W2 delta 1 norm of this second derivative. So this finishes the estimate on this Wn1 norm of this source term. In order to use this Nishimoto scheme, we also need to work on the energy estimate on the linearized equation. So in this case, if we assume under these assumptions, we can prove this energy indeed is controlled by the right-hand side. But it turns out we cannot work on the energy estimate as the formulation we did before. In our previous formulation, we needed to treat this term in the source term. But it turns out if we put this term in the source term, this term cannot be absorbed by the left-hand side when we work on the energy estimate. So instead, we have to put this term, when we work on the energy estimate, we have to work on energy estimate for the linear term on the left, with the left-hand side of this type. So like for instance, I give an example here. If you perform like energy estimate, H1 energy estimate, instead of multiply, take LT in the product of the original equation with Laplacian of x, you should take L2 in the product of this equation with divergence of the transpose the matrix times the transpose matrix of A times gradient of x. Then immediately you should find an inequality like this. Then for this term, by using equation by parts, you find a term like this. And also, by using the equation by parts, the main part of this term should be like this. So eventually, we should obtain an energy estimate of this type. Since this matrix A times this transpose matrix of A is a positive definite matrix, we can find this norm is almost like the H1 norm of gradient of x, And this is indeed the case by rigorous justification. And a crucial step to prove the convergence of this Nishimoto iteration scheme is to prove a decay rate, like gradient of xt. So the result is like this. This Hn norm of gradient of xt should decay to 0 according to the rate -1. So we should emphasize that like decay estimate of this type cannot be obtained by energy estimate. So instead we have to exploit this anisotropic lead-of-the-plane analysis and also this delicate dissipative properties of the linearized system. So if I have time, I'm going to explain. If I don't have time, I'm going to skip this part. So last step to work on this method is to use homogeneous version of Nishimoto iteration scheme. So first we should introduce a smoothing operator like this chi of t belongs to C infinity. Chi of t equals 1 for t less than equals to 1/2, and chi of t equals 0 for t greater than equals to 1. we denote this S1 of theta act on this y, be this kind of function, such that this t times t should be less than or equals to theta. For theta prime greater than or equals to 1, we also define this S2 of theta prime denotes the standard Friedrich's modifier. Standard Friedrich's modifier. So eventually, we define this smoothing combined version of cutoff operator with respect to time t, and also this modifying operator with respect to space variable in this way. S theta 1, S1 theta times S2 theta prime for theta and theta prime greater than or equals to 1. Now the scheme, we are going to solve this problem. Phi of y, ytt minus Laplace yt minus partial 3 squared of y minus fy. So we are solving this problem like phi y equals 0 with niche data like this, like y0 and y1. So in order to use Nash-Moser scheme, the first step, we define this y0 as the linearized solution of this system with niche data of this type. So now assume we already have the sequence y of p. How to determine yp plus 1? So in general, we can define the linearized operator L of p of x like this. In the usual case, here, instead of S of p yp, here should be yp. But now, because of this Nash-Moser scheme, we should replace this standard yp by this S of p yp. So here, this sp equals s theta p prime. And theta p equals 2 to the power p, theta p prime equals 2 to the power epsilon bar of p. When we prove the convergence of scheme, we will have to choose this epsilon bar later. So following this harmonic version of Nash-Moser iteration scheme, also see the paper, like similar paper by Kleinemann on CP 1980s and also AMRA papers in 1982, we can define this yp plus 1 equals yp plus xp, with xp to be a solution of this linearized system. So our next step, in order to prove the convergence, we needed to determine this g of p first. So in order to do this, let's denote this error ep prime by the replacement of this yp by sp yp. And ep double prime denotes this part, and we denote the error term eventually equals ep prime plus ep double prime. Then let's calculate this difference phi yp plus 1 minus phi yp, which equals phi prime yp x of p according to this definition. And we also write this xp as a solution of this like lp of xp equals g of p. So I just write like lp inverse of p. Now next step, we replace this yp by spyp. That's why we have a term like this here. And this is nothing but ep of prime. That's ep prime 2, g of p. So eventually we should have other result. We have this difference equals e of p plus g of p. By summation for this p between like 0 to p, we find this difference phi yp plus 1 minus phi y0 equals this. This formula will motivate us to choose this g of p. So eventually we choose this g0 equals minus s0 phi of y0 and a g of p in this way, which satisfies this inequality eventually. I still have 10 minutes, right? Okay. So I'm going to stop here because the other part is rather technical. I already put this part in a paper on archive. So if you are interested, you can check it from archive. Thanks a lot for your attention.